And I'm really excited to talk about like evaluations and challenges with them. 2 days ago, I talked about RLHF, but I must admit that like this stuff is my jam, and I'm stoked about it. I'm also really stoked to follow up Mary. I really liked Mary's presentation. I think you all should go and talk with her more because she's one of the best people in the world to talk about actual evaluations of AI systems. I thought it was a great talk. Unfortunately, like most of what I'm going to talk about is quite nicely destroyed with that. So whereas Mary focuses a lot on work involving like the substance and the practice of evaluations, most of the work that I do is focused on kind of the like technical tooling behind evaluations. So I'm going to talk about that a bit today, and actually what I'm going to talk about kind of comes in 3 different parts. I might have a little bit of time for your questions in between each part, but I'll try to reserve most questions, I think, for the end. So I'll get started. And the very first thing I want to kind of talk about is like overviewing different approaches by which audits are done. You might find this kind of interesting and helpful. I'm going to spend about like 6 or so slides on it. So these next few slides are kind of an attempt for me to like give a really loose taxonomy to some different ways that we like as a community understand AI systems. One way is through just anecdotes and people playing around with systems and talking about what they find with it. And it's really tempting to think that like anecdotal like studying systems is like relatively non-rigorous, or isn't like the best type of science possible. And by some standards, it's not. But for better or for worse, anecdotal demonstrations really kind of drives the epistemology of our community forward quite a lot. Here are just a couple examples of some really powerful anecdotes involving studying what AI systems can do. 2 days ago, I talked about the Microsoft research paper on the sparks of artificial intelligence, where they wrote an entire really influential and really popular paper, like just playing around with GPT-4, right? Same thing with the example involving paintshine that I mentioned 2 days ago. Marvin von Hagen found this really compelling and kind of arguably slightly field-changing example that inspired a lot of cool research and kind of changed the paradigm a little bit just by playing around with models. Aside from anecdotes, maybe moving up one level of rigor, we also have benchmarks, right? Benchmarks are another thing that like really, really unquestionably drives the field forward a lot because they concretize research goals and kind of spur up communities of people coherently working on very specific, very precise machine learning like challenges. Here's a great example kind of summarizing what the benchmarks are telling us about AI performance on specific tasks relative to humans. Without these benchmarks, not only would we kind of not know how progress is going very well, we also like probably wouldn't be able to make progress as fast as we are because we wouldn't have those concretized goals. One is like, it's really interesting to kind of think about how like benchmarks and an understanding of a field or subfield kind of lag a lot behind where the state of the art is. Something I think about a lot right now is how like poorly benchmarked lots of jailbreaking and robustness research is. And as we see stuff like this evolve, we also see like the benchmarking evolve. A third thing I'll mention is like red teaming and attacks. And there's, not everything I'm talking about is completely disjointed with each other, but I think it's worth a lot of emphasis here. Has anyone seen the panda image before? I bet like lots of you have, right? This is now like, we're now about at the 10-year anniversary of like this early type of experimentation with adversarial attacks against image models. And the arms race between adversarial attacks and defenses and understanding models through adversarial attacks and defenses is still like alive and well. I think this stuff is all still really relevant and cool. So red teaming and attacks is like another really important way we understand AI systems. We also use model transparency tools a lot. You all know about this stuff. Neil talked a lot about this stuff recently. And most people in the eval space who are really into machine learning are pretty excited about like potential prospects involving like doing good, high quality evaluations by using model transparency tools. I'll talk more about this very soon. Final kind of type of approach to evaluating and understanding systems could be through an audit. And an audit, like people have different definitions of it, so I'm just kind of like gonna use the term and think about things really broadly. What Mary was just talking about in the last section, which stems from lots of her work at GEM on evaluating models for dangerous capabilities, is at least using the methodology of what some people might call an audit. And I don't think Mary even mentioned this paper, like plugged this paper in her slides, which is pretty cool, but I'm a big fan of it, you should all check it out. There's another figure I wanted to slap up here from a recent paper by Hane et al., kind of trying to characterize like what different types of audits are done against lots of machine learning systems lately. It's another great paper. If you want the link to it, you can send me a message or something. And then the final thing I want to talk about, like the final type of evaluation approach is kind of forecasting societal impacts. And I think this one is worthy of like a lot of emphasis because it's kind of the real goal. Notice how everything I've been talking about up until this point in time is just kind of, sciencey, work inside a neat little box kind of work. But when it comes to trying to understand what AI systems are actually going to do in society, suddenly the problem gets a lot harder. Here, depicted up here is like one attempt from a paper with quite a few authors, including Irene Stahlheim, to just kind of put a framework around how we can think about studying the downstream societal impacts of AI systems, and it's like really, really complicated. I think someone asked Mary in the last question session, like, oh, are the threat models exhaustive? And Mary's answer was no. And one really, really concise sense, or concise way to explain how, in a sense, like lots of the threat models that like red teams work on are not exhaustive, is just by like pointing out that the real thing that we care about is the downstream societal impact of AI systems, but that's not very congruous with how what we study mostly focuses on kind of models in a vacuum, or specific kind of like demos or benchmarks. These are not the real goal. Right? And from this perspective, I think it's pretty useful to like remind ourselves that Goodhart's law is everywhere. And some versions of Goodhart's law might be really insidious when we think about like misunderstanding what impacts AI systems could have on society because we're not measuring exactly the right things in the lab settings in which we study AI systems, right? So Goodhart's law is everywhere. Here's an example from Zhuang et al. 2021. My advisor was on this paper. Kind of showing a great example about how as proxy utility goes up, when an imperfect proxy is used for a machine learning system, you see actual utility go down. And there's this certain kind of like key point here in which optimizing for the proxy stops even helping you to try to achieve actual utility. And there are a lot of versions of this when it comes to like evaluating AI systems in lab settings when what we really want is to understand how they're going to affect the real world, right? Think about like benchmarks. Benchmarks are very, very, by nature, kind of concrete. If you think about a benchmark like HarmBench or glue or superglue, it's trying to measure something that's like easily measurable, even though the societal impacts of the AI system are not very measurable. So we can fully expect that if we optimize for like benchmarks involving performance or benchmarks involving safety, there are still going to be gaps between, I'll take questions at the end. There's still going to be gaps between like what we think we know about the AI systems and how little we actually might know, right? And there might be points in which we start to over-optimize for a proxy and it starts to actually become harmful toward our actual goal. Another version of this that happens with societal impact forecasting, societal impact evaluations, is a problem that stems from like inclusion. There are like lots of different people in the world, and with representing lots of different viewpoints. And when we train AI systems, they're going to have impacts on the world that not everybody is going to like agree with or think is good, right? And Goodhart's law applies to this too. If our evaluations aren't kind of inclusive of different types of viewpoints from different people in the world, we can fully expect that at a certain point, once we start to like over-index on proxies for how AI systems are going to affect the world, like what technocrats who organize evaluations are kind of focused on, we can fully expect that like at a certain point, alignment could become a threat to people who are kind of excluded from the alignment and evaluation process. And lately, I think there's a really important kind of thesis about how, AI alignment kind of demands inclusion and nuance and detailed analysis. That's the first subsection of stuff I wanted to talk about. And maybe if there's one question, I can take that, but I might kind of try to keep moving forward. Yeah, sure. Thanks for passing the mic.
Yeah, Is this also consistent with grokking or this double dipping phenomenon? So that would we see this dip in utility even if we keep on iterating?
There might be instances in which some grokking happens with an ML system, and what a curve like this, involving proxy versus actual utility, does kind of like changes qualitatively. But that would probably, stuff like that, like most examples of grokking would probably be like an interesting special case. I think the Goodhart's law phenomenon here is the real point to make. I think analogies with, or like thinking about things in terms of grokking, is not something that I know of a lot of like motivation to do. That being said, different curves for different models solving different proxies in different settings are going to look different. I'll go ahead and move on. So I'm going to take the second, this part 2 of 3 of what I'm talking about today, to kind of talk about some work I've recently done on challenges involving doing AI evaluations without a lot of access to the model. I'll talk more about what that means in a sec, thanks to a lot of co-authors up here. Let's move on. So historically, AI research has benefited a lot from transparency. I think there was a question, last question session to Mary, about like thoughts on the open source versus closed source AI. And there are like definitely pros and cons here, but one historical benefit of like open source AI systems has been that researchers get a lot of opportunities to like understand what's going on, and society benefits a lot from that. For example, if you want to go work with like the BERT model, almost all of the relevant information for like training and from the developers of that model is on archive. The code is on GitHub. There's a lot of benchmarking done, and models are released on Hugging Face, right? So it's really easy if you're a researcher to go and like study BERT or something. But just as at the same time that evaluations are getting much more important, and we're starting to get more worried about the societal impacts of AI, we're seeing this unfortunate like kind of decrease in the degree of transparency that is available for researchers to study systems. And I'm not out here kind of like saying that things are unbalanced bad here, but this is certainly at least a perverse subdynamic of the time that we're in right now, where like today the state-of-the-art AI systems are closed, whereas they didn't used to be, and that makes a lot of challenges a lot harder, right? And this is also happening at the same time that everybody is talking about audits, and everybody is saying that they love audits, right? Like different governance frameworks, position papers, voluntary commitments, all kinds of stuff like this. Everyone loves audits to the point of kind of suspicion. Even the companies and organizations who are supposed to get audited at least profess that they love the idea of audits, which is really interesting, right? And one way to partially explain this somewhat counterintuitive observation involving how everyone loves audits comes from how not all audits are created equal, right? Not all audits are going to like apply equal types of scrutiny. Meanwhile, regulatory frameworks have really been designed to rely on effective audits. There are examples of this in the US, the EU, and the UK. There are also some examples in other like municipal governments. There's at least 1 or 2 examples I've seen from China, but I didn't include them on this slide. So how do we get more effective audits? I think one really important concept to understand here is that like access is a really core aspect of an AI audit. And a very concrete and very concrete claim that I'm very comfortable making, even though I'm not comfortable making that many claims about how audits should be done, is that in order to understand the outcome of an AI audit, looking at the raw results of the audit or the raw findings of the audit alone are not sufficient. Something else that you need, probably among other things, to understand the outcome of the audit is what the auditors were doing and what they had access to, what they tried, and what was kind of like in their option space when conducting the audit, right? So in AI, we have, or when working with like machine learning models, we have these different notions of like black, gray, and white box access. Probably everyone's familiar with this, but like a black box system, you can only see inputs and outputs. A gray box system, you can see some limited amount of information involving the system internals. And with white box access, you can get full access to the system. Right? Meanwhile, there's also another really useful concept that I like to think of as outside the box access, and this just kind of means everything else, right? So an auditing team, for example, with outside the box access might have access to like source code, or might have access to the data that a model was deployed on, or a report from internal evaluations, or an understanding of methodology, right? All of these count as like relevant forms of access when it comes to trying to understand what a system is doing, right? And there's a pretty easy point to argue, following from this, involving how better access, all else equal, is going to allow auditors to do a better job of understanding what's going on in the system, right? And the TLDR of the next few slides that I'm going to talk about is this, right? For audits to be effective, they need to be high quality, and for them to be high quality, auditors need access. Transparency regarding the access and methods used by auditors is necessary to properly interpret results. And white and outside the box access allow for substantially better audits than black box access alone. And these types of claims are actually not the most unique to AI systems. I also like to imagine a lot of the times like a mechanic trying to assess what might be going on with a car if they're not allowed to open up the hood, or a software engineer trying to debug the code without being able to look at it. I think some really obvious analogies kind of apply here with like audits of the machine learning systems. So we wrote a paper. That paper was in the slide earlier. And it's called Black Box Access. Is it sufficient for rigorous AI audits? And the main substance of the paper was kind of summed up best in this table, when we do our best to overview what different types of like algorithmic techniques are involved, or can be involved in audits, and what's possible with different forms of access, right? Whenever I talk to people about this paper that we worked on, usually the first question that I get is like, oh, does that mean that you are talking about using interpretability for AI system evaluations? And then I'm like, well, yes, that's one of these check marks in the table here. But in general, like, there's kind of a lot more to the picture. You know, you can do some really, really useful things with black box evaluations. And I think the majority of what Mary talked about was, in the last session, is kind of focused on this kind of stuff. And there's so much like awesome stuff going on with black box evaluations, and I think that's really, really cool. But you know, our community is also one that cares a lot about model internals as part of many like important research agendas involving AI safety and alignment, right? And that's kind of where like lots of this comes in. If you have gray box access, you can start to do a bit more. But if you have just white box access, you can do quite a bit more when it comes to what types of attacks you can administer against the system, what types of ways you can interpret the system, whether or not you can fine-tune the system. And there's a lot of work under like all of these things kind of showing, in the literature out there, kind of showing the potential for lots of usefulness by using these sorts of techniques to evaluate AI systems. You'll notice there's this distinction between de facto white box and white box. What am I talking about here? I'll get to that more in a few slides, but TLDR, de facto white box access is something, it's like a very light gray form of access that allows auditors to do like everything that they want to do, except for copying the model parameters. Talk more about that in a minute. But then also there's outside the box access, right? And needless to say, there's a lot of really useful stuff that you can do, including like data evaluations and stuff like that. So I hope this table kind of goes to show, or summarize at least, some of the nice things that you can do with privileged access when you're auditing AI systems. And this is mostly where the substance of the paper we wrote kind of comes in, but I'm just spending one slide on it, because I want to focus on some more high-level points. So, I already talked about mechanics and software engineers. There are some examples in AI in which black box access is like empirically very limiting. Last year, a best paper award at NeurIPS went to Schaefer et al., who showed that like lots of the discussion around emerging capabilities in large language models that happens with scale is like really based on incorrect assumptions and kind of naive. And things get a lot clearer when you start looking at logits instead of just raw model outputs. I think that's a great example of like how black box access can not just be limiting, but even misleading. Natural adversarial examples. I won't spend too much time on that. let's focus more on advantages of white box access. So this is just a summary slide. It's just in text. It's already boring. But most of the nice things about white box access involve how white box attack algorithms are more efficient, white box interpretability tools can aid in diagnostics, and fine-tuning can reveal risks from latent knowledge of post-deployment modifications. I want to talk more about fine-tuning soon, so put a pin in that. Insert AI-generated image. So meanwhile, with outside the box access, there are also some nice examples about how the code, documentation, and hyperparameters help auditors work a lot more efficiently. Access to methodological details helps to identify risks. Access to data helps to trace problems and assess fair use. And contextual information makes it easier to hold the developers accountable. And with all of this stuff and the stuff on the last slide, I think these are all pretty compelling reasons to think about how, when we design AI audit regimes, when we start to ask the questions about like who the auditors are, who pays them, what they do, what they look for, who decides what they look for, and what incentives they have. And it's really important to think about how to give good answers or good resources to auditors so that they're able to do their jobs as effectively as possible. Because as I talked about earlier, regulatory frameworks are being designed to rely on high-quality audits. All right. Oh, I forgot about this slide. Should auditors be able to request technical assistance? If developers act in good faith, maybe. But I'm going to skip that slide mostly. So I told you earlier that when I talk about this paper, I'll talk with people about this paper, the first question I always get is, like, does that mean you want to use interp tools for evals? My answer is yes, but. But the second question I always get whenever I talk to people about privileged access audits is like, but the labs are never going to hand over access to the models. That's a huge security and IP risk. Could this ever feasibly happen? And the answer is that like there are some ways to help it happen. There's a lot to be learned from other industries in which audits happen. And the model weights never need to leave the developer's facilities. The model weights never need to leave the developer's facilities. So what can we do to make sure that audits audits with privileged access are still done securely? There are kind of three techniques here that I think are really useful to think of. One is technical, in which we use APIs, right? And APIs are one way of giving what I called earlier as a de facto white box access. For every white box process, there is a gray box API that can perform that process on a model remotely without returning model parameters or equivalent information to the person running that process. An example, there's a thing called a flexible query API, don't worry about it right now. A great example of this, and a much more simple one, is how people can just go and fine-tune GPT 3.5, right? There's an API for that. And fine-tuning is a process that sees all of the weights of the model and updates all of the weights of the model, right? But this can still be done without OpenAI sending you all the weights of GPT 3.5. So in fact, this API could be designed, as very analogous to how many other types of APIs could be designed for many other types of white box processes. A second way to address these concerns, in addition to technical solutions, are just physical solutions involving secure research environments. That basically just means that auditors can go onto the campuses of developers and work from there without like taking in a jump drive or taking out a jump drive or something, right? And in this way, an auditor would be a lot like an employee of the company and wouldn't necessarily incur any risks beyond what employees already incur involving intellectual property. There's also legal strategies, right, that are precedented in other industries, like auditors can sign non-disclosure agreements. Auditors in other fields also frequently sign agreements that prevent them from working for a competitor of a company that they audited for like a number of years or something. And in that sense, if you combine this with like physical safeguards involving secure research environments, something you can get is potentially auditors that pose less of a risk to this IP security of a company that they audit compared to the company's own employees, right? In lots of fields, all the time, employees of one company will get headhunted by another company that's competing with them, right? But in many of the same fields, this cannot happen with auditors, at least not legally, right? We can do the same thing in AI. Nice, okay. Oops, I messed up my transitions. My favorite things to talk about when people are asking me about like the security of audits is like harder problems that like humanities governments have already solved before. I think one great example is the USDA, the Food Safety and Inspection Service. You know, the United States federal government has collectively decided that contamination in meat products is a big enough problem in order to have a workforce of like 11 or 12,000 food safety inspectors who work on site at lots of like meat processing and packing facilities across the country in order to ensure quality control. Another, even more dramatic example is the International Atomic Energy Agency, which is employs, I think, over 300 different expert inspectors from over 80 different countries who go around the world and inspect nuclear facilities for safety. And during these inspections, they are on site. They can be sometimes unannounced. They can involve auditing the facility's accounting and operation records and verifying things about like what the company is doing like behind the curtain, right? Which is analogous to using kind of white box and outside the box access, which is pretty cool. So this is usually my response when people are worried about like security and audits, because humanity has just solved bigger problems before, but in other industries. And hopefully we can do so with AI. Because if food poisoning is a big enough threat to like humans in the United States to warrant, you know, as much as the USDA does about it, hopefully threats from AI are enough to warrant, you know, being creative enough to do like good, well-resourced audits. There's some worry that black box audits might happen by default, and this is one of the reasons why I try to like emphasize like how possible white box and outside the box audits are. There's a lot of precedent for it, and there are developer incentives against constraints and scrutiny. There's also this like potentially insidious dynamic, because the view that looking under the hood isn't worth doing with these models is mutually reinforcing with public ignorance about what is under the hood. There's one empirical example that I think is like pretty striking from 2021 involving lobbying, involving an early processing on the EU AI Act in 2021 by Google, where Google submitted a proposal for consultation where they claimed, and in context there's no justification for this claim, it was actually kind of rather baseless, and something that I speculate was written by technical people to confuse non-technical people. But they claimed that there will always be better methods for verifying the performance of an AI system, such as input-output auditing, than direct access to source code, rendering a provision about access to source code in a draft of the EU AI Act superfluous. And that would be a really interesting claim if it were true, or if it were backed up by any like additional argument inside of this point inside their consultation, but it was not, and it was not really true. So I think we gotta like be really vigilant about this stuff. We gotta be like we gotta watch out for like market forces at play that could lead to harmful forms of regulatory capture here. I'm going to not spend a lot of time on this slide, but you know, policymakers can consider useful stuff here. Another really important point to make is that I've been focusing a lot about challenges with audits involving access, right? But audits can fail for a lot of reasons, like poor resources, limitations of technical tools, narrow scope, conflicts of interest, exclusion of underrepresented viewpoints, cosmetic compliance, and regulatory capture. You know, it wouldn't be possible for one to make an entire slideshow on any of these things. Unfortunately, I'm only really qualified to give the slideshow that I'm giving right now. So do it that way you will. And now I want to move on to part 3 of 3, and I think I have about 10 more minutes. Are there any questions while I pull up the next set of slides? Yeah, can we do that one there? Thanks for passing the mic.
Okay, I was wondering, you said it for almost, or for any white box method, there exists some, you can develop a gray box method which would solve basically the problem. But then you create a problem of auditing the API actually, right? That like the middleman between the black box behind. How would you do that? How would you,
Yeah, another way of describing this is that like this challenge is that if you're doing an audit through a trusted API, you have to ensure that that API is secure, right? And the API in this case is usually going to be designed by the developer. So another way of framing this problem is like, how do we make sure that the developer doesn't commit fraud, right? And this is something that all sectors in which in which audits and oversight are kind of like done. This is a common problem with all kinds of stuff like this, and the answer usually involves like, scrutiny and heavy penalties for when fraud is done. Another reason for this challenge is that another way around this challenge is to just do like on-site access. I'm a really big fan of taking out the middleman and just having auditors go onto a developer's campus in order to get unrestricted access. That's pretty nice. Okay, great question. I'm going to keep moving on. So the last thing I want to talk about is kind of one way that I've been thinking about a lot recently, involving trying to kind of raise the bar for how we do audits and evaluations in ways that are kind of like more sensitive to certain types of hard to foresee risks, right? So lots of my thinking in this space is motivated by some persistent challenges with AI. And I actually want to start this off with a joke, or what I thought was a joke back in 2021. So our friend at Harvard CogSci, Tomer Ullman, made a very wonderful observation where he said that after few-shot, one-shot, and zero-shot learning, the next frontier for AI/ML is clear. Negative shot learning, where the machine keeps saying it's a cat even though you beg it multiple times to stop. And in 2021, I was like, I was so naive. ChatGPT wasn't out yet. The world was a so much simpler place. And I just thought that this was like a funny, hilarious example of comedic, infantile extrapolation. And now in 2024, I'm like, oh shit, wait, that might not have been a joke. Because we do have negative shot learning problems, where the systems keep doing stuff that we explicitly fine-tune them not to do. But instead of saying something's a cat, it's giving instructions for making bombs, right? So I recently, my list isn't up to date, but I've recently been trying to curate a list of different papers from the jailbreaking literature that have all shown different ways, a variety of different ways of getting AI systems to give you instructions for making bombs, right? And this is a persistent problem. Papers keep doing it. The most cliche thing possible that a red team could do, red teams still keep doing successfully even as new models come out. And I think this is a pretty big concern. I think the model that this leads me to is kind of thinking of AI red teaming and trying to find problems with models through audits or other evaluations as a game of carnival ring toss, right? And in a game like this, you have many targets in front of you, many different models, and you're trying to throw a ring to capture some of them. And usually in a game like this, it's super strict and you miss most of the time, right? But sometimes you're lucky enough to kind of get a hit. But when you do, you've gotten a hit. But in this analogy, the real problem is trying to find all of the bottles, which is pretty big challenge. And for this reason, AI red teaming empirically seems to be a lot like a game of whack-a-mole. When we find problems and we're trying to fix them, usually that doesn't generalize to all of the problems, and there are many more to be found. A good example of this comes from the last few weeks. There's this organization that's new called GRACE1 AI. And don't get me wrong, GRACE1 AI is awesome, and I'm a huge fan. And they're pretty new, and one of the first things that they did upon launch was releasing their model called Signet, which is a fine-tuned version of Llama 3.8b that has kind of state-of-the-art robustness against jailbreaks. And it's awesome. It does have state-of-the-art robustness against jailbreaks, that much is true, but there are still jailbreaks for it. And then people on Twitter jailbroke it day one after it was released. And the people of GRACE1 AI were like, yeah, we know there exist some problems, and the point of the release was to understand more problems and advance the science here. So, GRACE1 being pwned or whatever, isn't exactly the right conclusion to take away from this. I think this is a bit overly emphatic. But here's this great example, and I was talking about some of this 2 days ago as well, where our state-of-the-art attempts to try to make models basically safe can still seem to just persistently fail once red teamers kind of do their thing, right? The arms race is alive and well. So I think in light of this, the persistence of lots of failure modes in LLMs and how they persistently exhibit a lot of problems like this, we kind of might need to rethink how we evaluate and fine-tune AI systems for safety, because the emerging understanding seems to be that the model, which is we can view as a tentacle monster or something, has really nice outward behavior in those situations, right? But that kind of conceals a lot of bad latent capabilities that can pose risks if they resurface. Right? Let me talk a little bit more about this emerging consensus. There's a bunch of evidence from the jailbreaking literature. There's so many things I could quote here, but a survey paper last year talked about how even safety-aligned LLMs could be susceptible for adversarial jailbreaking attacks, even SIGNet, like I talked about a few slides ago. The continual learning tells us the same thing. Fine-tuned language models can be continual learners. They're a lot like elephants. They never really forget things, or at least it's pretty hard to make them forget things once they've learned them in pre-training. And techniques like RLHF are pretty bad at deeply removing harmful knowledge from models in the way that we would want them to. There's a bunch of evidence from the model editing and representation engineering literature, right? Removing regions involving safety guardrails compromises safety without significantly impacting utility. There's evidence from the MEC-interp literature in which even when some information has been unlearned from a model superficially, correct answers can still be probed for using the model's internal representations. There's more examples from MEC-interp and also fine-tuning literature in which Jane et al. Concluded that fine-tuning rarely alters the underlying model capabilities. A minimal transformation, which we call a wrapper, is typically learned on top of those capabilities, and further fine-tuning leads to sample-efficient revival of that capability. The few-shot fine-tuning literature tells us the same thing, in which Chi et al. Jailbroke GPT 3.5 Turbo safety guardrails by fine-tuning it on only 10 examples, making the model responsive to nearly any harmful instructions. So I think the verdict we have is that LLMs are really good at retaining unwanted capabilities that we try to fine-tune and adversarially train out of them. And these capabilities being kind of relatively rare in normal circumstances does not prevent them from being pretty harmful when they do resurface from something like an attack or an anomaly or a post-deployment modification. So what do we do with how we train and evaluate models to try to get around this problem? Oh, sorry, by the way, if you want any of the references I just talked about, you can send me a message. Okay, so what do we do? I think something that we might see soon is a shift toward generalized attacks for adversarial training and evaluation. The analogy here is really clear with a lot of other safety-critical engineering fields. It's really common in safety engineering practice to design systems to be robust to stresses and pressures that are at least as powerful and ideally more powerful than ones that they're ever meant to face in deployment. Right? Imagine that I'm going to go rock climbing with a friend of mine, and this rock climber friend gives me a rope, and it's a weird rope, maybe one that I haven't seen before. And maybe my friend tells me, okay, Cass, you look great rock climbing on this rope. What are you, 170 pounds? I tested this rope's tensile strength up to 175 pounds, so you should be great, right? But after that, I don't know, but at least you're 170 pounds, so it's fine, right? I don't think I would climb on that rope. I wouldn't feel great about it, right? And the problem's even kind of worse in the real world, right? Not only are evaluations of systems not necessarily stronger than the pressures that they'll face in the deployment, sometimes they're a lot weaker, right? Llama 2 is a really good example of this. If you go to the Llama 2 paper and you read the section on their evaluations, they don't talk about model manipulation attacks, right? They just talk about the black box red teaming that they have red teamers do. And then they proceeded to open source their model anyway, and then people have been able to fine-tune Llama 2 into doing a lot of things that arguably they shouldn't have been able to do so easily, right? So there's a lot of precedent for actually the opposite of what we want, for systems being evaluated under weaker threats than they will be placed under in practice, right? All right, so generalized attacks, what do I mean by that? The two most salient type of generalized attacks are latent space attacks and few-shot fine-tuning attacks. In general, a generalized attack is just an attack that uses greater permissions than, or it uses more levers to do mischief with the model other than designing an input that makes it fail. A generalized attack, like a latent space attack or a few-shot fine-tuning attack, these are model manipulation attacks, right? Latent space attacks manipulate internal activations, few-shot fine-tuning attacks can fine-tune the whole model, right? These are things that I think are going to be really, really interesting, and we're starting to see this in the adversarial training and adversarial red teaming literature now. So I'm going to spend the last -1 minutes of my time to just talk a tiny bit about latent adversarial attacks and latent adversarial evaluation. And if you like this little thing on the right here, I have a bunch of stickers. So if you come up to me, I'll give you a sticker. So I work a lot on latent space attacks, mostly in context of latent adversarial training so far, but soon in context of latent space adversarial evaluations. But the nice thing about latent space attacks is that they leverage abstract representations. We understand that models, as they propagate information through them, develop representations that happen at an increasingly higher level of abstraction, right? And the key insight behind them is latent adversarial attacks can activate neural circuitry involved in failures without requiring inputs that trigger them, right? This is very nice because of this problem. And this one figure can actually motivate lots of AI safety and AI alignment research to date, right? There are many, many inputs to models, absurdly many inputs, way too many inputs to thoroughly search over with a brute force search. For example, there are more 10 by 10 grayscale images, and more than there are particles in the universe, and it's not even close. There are also more 20 token sentences in English, using English tokens, than there are particles in the universe, and it's also not even close. So we're never going to be able to brute force ensure that models are safe. Instead, what we try to do, and what really awesome teams like Larry's are doing, is trying to be a red team, or try to identify all the problems one can using lots of heuristics to kind of target relevant things that might make them well fail. But there's always going to exist a gap because of the sheer size of the input space between failure modes the developers identify and ones that they don't. So something to motivate generalized adversarial attacks is by trying to help us do adversarial attacks that kind of relax the typical box that these evaluations are done in, so that we can get a better idea of what failure modes might exist that are just hard to find. So that's the idea here. Latent space perturbations can do strictly more to a model than input space perturbations, right? And you can elicit more through a model by fine-tuning it before attacking it than just by attacking it alone, right? So this is the motivation. I think I have one more slide. Well, no, I have several slides, but I'm going to take a few seconds on each. So some collaborators and I did some past works on latent adversarial attacks, and found some really promising results in which they could help with generalizable robustness a lot. And there's also some current work that hopefully, if we're good, we'll put on archive by the end of the day, involving how you can improve over some state-of-the-art alignment techniques using latent adversarial training. There's an example here that I won't have enough time to go into detail about, but we basically find that latent adversarial training can be a solution to the sleeper agents problem, if any of you are familiar. And my last slide is that some stuff I'm working on next is trying to link generalized adversarial threats and input space adversarial threats. So a hypothesis that I'm actively working on, and something that I hope could be really interesting for the model evaluation literature, is trying to understand if robustness to latent space and few-shot fine-tuning attacks can predict a model's robustness to input space threats that are potentially hard to foresee. And if they can be, I definitely hope that they could make their way into the model evaluation toolbox sometime. So overall, that's my last slide. So I'll just kind of end by saying thanks for all the time and the attention. And if you want to talk with me more about anything, especially something that I kind of skipped over, find me soon. I think right after this next lightning talk session. And I think I'll shift over the time so we can start on